Dear friends, welcome to a lecture on complex analysis. In this lecture, we shall study limits of functions of complex variables. Earlier, we have studied limits of real valued function, and the concept is similar to that of real valued functions. So, we shall just revise what is the definition of limit of real valued function, and the basic definition is epsilon delta definition. Say, for real valued function, we have studied this in real analysis. We say a function f of x has limit as x tends to a is equal to L. And what is the epsilon delta definition? Epsilon and delta are Greek letters used for small real numbers, to denote small real numbers, positive, small positive real numbers. And here the definition is given epsilon greater than 0, there exist delta greater than 0, that is small positive numbers such that the distance between fx and L, or which is denoted as mod of absolute difference of fx and L, mod of fx minus L, is less than epsilon whenever the distance between x and a is less than delta, or whenever 0 is less than mod of x minus a is less than delta. Here x may not take the value of a, and therefore this is deleted neighborhood. Earlier also we have seen what is deleted neighborhood. Those points which are within delta distance from x, delta distance from a, are considered in this neighborhood. Or if you consider a diagram for this, then suppose these are the values of x and its images are in this set. So the function is f, and suppose the image of x under f we have denoted it by f of x, and let x approaches a, this point is a. As x approaches a, then the function will approach towards a value L, and it is here. So fx then will approach towards L. When x is closer and closer to a, this is the meaning of x tends to a. As x tends to a, f of x will tends to L, or f of x will approach towards L. Or that means whenever the distance between x and a is becoming smaller than delta, this distance is delta, and whenever or smaller than delta, then the distance between fx and L is less than epsilon. So this is the meaning of function of real valued, that is real valued function f of x as x tends to a. Now the similar concept is there used to define limits of functions of complex variables. Instead of f of x, we are considering function as f of z. Let a function f be defined at all points z in some deleted neighborhood of z naught, and that means we have seen delta neighborhood of z naught, those points z which are within delta distance from z naught, or that is, this is the delta neighborhood of z naught. We say limit of the limit of f of z as z approaches z naught is a number w naught, and if for each positive number epsilon, so and this positive number is not fixed, it is arbitrary, any positive number epsilon that we have to consider, there exists another positive number delta, both epsilon and delta are greater than 0, such that absolute difference of f of z, or absolute value of this difference f of z minus w naught, is less than epsilon whenever this absolute difference or absolute value of z minus z naught is less than delta. 0 less than mod of z minus z naught is less than delta. Why here z is not to be taken as z naught? Because the function may not be defined, or function will not attain the value at z is equal to z naught. So in the neighborhood of z naught, we have to find what will be the value of f of z, and that value will be close to w naught. And this is written as limit of f of z as z tends to z naught is equal to w naught. You may see the similarity in this definition. Here the function is denoted by f of x, the limit is L. Absolute difference of fx and L is less than epsilon whenever the absolute difference of x and a is less than delta. That means first this happens when x is close to a, then its image f of x will close to L. And here what delta depends on epsilon and the function. As epsilon changes, delta will be changed. If you make epsilon smaller, then the delta will also be taken accordingly as smaller value. And if a result holds for this less than delta, then it holds for a smaller value than delta. Epsilon is arbitrary. We can take epsilon as any value, positive value. Epsilon may be 0.1 or epsilon may be 0.01 or 0.001, etc. Or in sometimes we can replace epsilon by 2, epsilon by 10, etc. So it is not fixed, it is arbitrary. Epsilon and delta are positive numbers, positive real numbers, and these are Greek letters used to denote positive numbers. So these are the relative changes. Here when x is approaching towards a, x becomes closer and closer to a, f of x becomes closer and closer to L. And in this case, for functions of complex variables, f of z function will approach towards w naught, and that means the distance between f of z and w naught is less than epsilon, and this happens when z is close to z naught within delta distance, that is z lies in the delta neighborhood of z naught. Now we shall show this as in this like this, as in figure. We consider two planes separate, say one for z and another for f of z. See, suppose this is the z plane, and we may have this as z naught, this point as z naught, deleted neighborhood, and suppose this distance or this is z naught we have considered, and center of this z naught, and this is delta, and z lies in this neighborhood, that is distance between z and z naught is less than delta. This is deleted neighborhood of z, a deleted neighborhood of z naught. And now what we will have, the image will be like this. In UV plane, and the image of z will be f of z, and z naught, f of z naught will approach towards w naught. So now the another neighborhood will be there of radius epsilon, and its center is w naught, and radius is epsilon, and that means f of z is in this neighborhood. F of z is in this neighborhood. For every values here in this neighborhood, the distance from w naught is less than epsilon. So whenever z is within delta distance from z naught, f of z will be within epsilon distance from w naught, and That means this happens first and then corresponding changes will happen in this function's value. So this is the meaning of limit, or actually this is the definition, epsilon delta definition of limit. So the concept is somewhat difficult to understand, but you can see the meaning of it. So here epsilon delta are the letters used to define limit of a function. Now we will have an example how to use this definition to show limit of a function is the given quantity, and this limit is denoted by limit z tends to z naught of f of z is equal to w naught. See, limit of f of z is w naught as z approaches z naught. Now we will have an example, and then we shall show that limit is unique. So use definition of limit to show that a function f of z, which is I z bar divided by 2, defined in this open disk mod z less than 1 has limit z tends to say 1 of f of z is equal to I divided by 2. So this is that we have to show limit of, this is the function given, I z bar conjugate of z divided by 2 is the function defined in the open disk mod z is less than 1, means circle having center at origin and radius is 1. So z lies within that neighborhood, has limit z tends to 1 and f of z is equal to I by 2. So this is the example. Now we shall show this limit using the definition epsilon delta definition. So here we are asked to use definition, and now the solution, how to use the definition to show limit of a function. See, solution for this. What we need to find is the value of delta. This condition must be satisfied. For each positive number epsilon, there exists a positive number delta satisfying this condition. So we have to find for every epsilon, every positive number epsilon, we have to find, or we have to show that there exists. If we could show this condition, then we can say limit of f of z is equal to w naught, and that means for given every epsilon we have to find delta which satisfies the condition of limit for this. So we have to show that there exists, or actually we have to find there exists a positive number delta such that absolute value of f of z minus I by 2, this is w naught. See, this is w naught and we have to use the definition, and this is f z minus w naught means f of z minus I by 2 and is less than epsilon whenever 0 is less than the neighborhood of, and what is the point here? It is 1. So z tends to 1, z minus 1, and is less than delta. This is what we want to show, and we shall suppose this as statement 1. Then we are done. The function is I z bar by 2, f of z. Or now I shall rub this part and write here. See, what is f of z? Now we will consider this condition, and we will obtain delta. So now what is f of z minus I divided by 2 less than epsilon? That is, what will be f of z? F of z we have here considered as I z bar divided by 2, and therefore we will put this value here, I z bar divided by 2 minus I by 2 is less than epsilon, and this means from this we can take I by 2 common under this absolute value, and that is by using the properties of absolute value function. We can take common, and we have these properties z1 z2. Absolute value of z1 z2 is absolute value of z1 into absolute value of z2. So I by 2 is common, product is there, and in second part it will remain z bar minus 1 is less than epsilon. Again, that is, now what is the absolute value of this I by 2? Again we have this result is absolute value of z1 divided by absolute value of z2, and absolute value of I is 1, absolute value of 2 is 2. So therefore this is 1/2, this is 1/2, and this can be written as z bar minus 1 is 1, the absolute value, see 1 and 1 bar, the absolute value will be the same, since the reason for this is, since absolute value of I is 1 and absolute value of 1 bar is 1. Absolute value of conjugate of 1 is 1. Conjugate of real number is itself, and therefore we can replace this 1 by conjugate of 1. Simply conjugate of 1 is 1. 1 is equal to 1 conjugate, and that is less than epsilon. Again, that is half, and this E can be written as conjugate of z minus 1. That is again conjugate of z1. See, this is since z1 minus z2 conjugate is equal to z1 minus z2 conjugate, and this is less than epsilon. These are the reasons for these left side steps, and again, so this is half mod of z minus 1, absolute value of z minus 1 is less than epsilon, since absolute value of z bar is same as absolute value of z. So we can have this equal, and what this suggests here, multiply by 2, or that is z minus 1 is less than 2 epsilon. We have multiplied both sides by 2, inequality remains the same. And again, what is given is this mod z is less than 1, and therefore z is not equal to 1. It is absolute value of z is less than 1. Z minus 1 will not be 0, and that means it is greater than 0, or 0 is less than z minus 1 is less than 2 epsilon. Since we have mod z is less than 1, it is given in the problem, and thus this, after simplifying this part, we obtained the value of z minus 1, absolute value of z minus 1 is between 0 and 2 epsilon, and same condition is here. You see, 0 less than mod z minus 1 is less than delta, and that means this when this is true, the first inequality will hold, and that means when this condition is satisfied, this condition is satisfied, and by comparison you see we can select delta as 2 epsilon, and therefore if you select delta as 2 epsilon, this condition is satisfied by this delta, and thus there exists delta which can be taken as 2 epsilon. So therefore if we take delta as 2 epsilon or smaller than 2 epsilon, if we take delta less than or equal to 2 epsilon, or there we want to show that there exists a positive number delta, and that delta can be taken as 2 epsilon or smaller than 2 epsilon, then this condition 1 holds. Then we have mod of f of z minus I by 2 is less than epsilon whenever zero less than mod z minus 1 less than delta. Delta is 2 epsilon, and thus this shows that the statement 1 holds, and if the statement 1 holds, we can say limit of f of z as z approaches 1 is equal to I by 2. This shows that, or this proves that. So we have obtained delta is equal to 2 epsilon or less than 2 epsilon, and thus our purpose is served, because we need to find delta, and we have obtained such a delta satisfying this condition according to the definition, and therefore this proves the limit. Now what is the meaning here in diagram form? See, z approaches 1 and z is within mod z less than 1. So if you draw a figure for this, then it will be like this. See, we have mod z less than 1, and that will be a circle having center at origin and radius 1. So this is what is mod z less than 1, and 1 will be this point here, deleted neighborhood. 1 is not included in the neighborhood because z cannot take value 1, and this is mod z less than 1. You see, and what about the delta neighborhood of 1? This 1, delta neighborhood of 1, yes, and that can be shown like this. Delta neighborhood of 1, and what is delta? Delta is 2 epsilon. We can take delta is equal to 2 epsilon, and but z must satisfy these conditions. Z is less than or equal to 1, and z is in this neighborhood, and z is less than or equal to 1 is z lies in this, within this circle, and z also must be in this neighborhood, and condition is satisfied, both the conditions is satisfied by this z lying in this region, or we may show like this shaded region. Z lies in the neighborhood, z lies in the circle, within the circle. And now what about the value of the function? Function will approach towards this I upon 2, and it is epsilon, see, epsilon neighborhood of I by 2, and I by 2 is a point on imaginary axis phi, and this will be I by 2, that is half unit, and that is I by 2, and we may have the epsilon neighborhood of this. So this is epsilon, and this is f of z. F of z lies in this neighborhood. Distance between f of z and I by 2 is less than epsilon whenever the distance between this 1 and z may be any point here. Distance between 1 and z is less than 2 epsilon. So in this way we can use the definition of limit to show the limit of particular function is given value. Now we will prove one result, that limit of a function, if it exists, is unique. As a theorem, limit of a function fz f of z, if it exists, is unique. Means only one. A function cannot have more than one limit. It has only if it exists. Sometimes function limit may not exist if the condition is not satisfied, and if the condition is satisfied, the limit exists, and if the limit exists, it is only one. Now to prove the theorem, what we shall assume is, suppose limit of this function f of z, as z approaches z naught, having two values. Proof of the theorem: let limit z tends to z naught of f of z is equal to w naught, as in the definition earlier, and also let limit z tends to z naught of f of z is equal to w1. Let us suppose there are two limits, w0 and w1, and then what we will prove is w0 is equal to w1. That means there exists only one limit. The two limits are equal. Now by definition of limit, we will apply the definition of limit for both these limits. So by definition of limit of function, limit of a function, we have given for every epsilon, every positive number epsilon, there exists positive numbers delta naught and delta 1, such that, why we have considered two positive numbers, because we have assumed two limits, and delta naught is a positive number related for first limit, delta 1 for second limit. Epsilon we have taken the same, and but you see, we will write the result as for the first limit. See, f of z minus w0 is less than epsilon by 2. Epsilon is arbitrary, so every epsilon the result holds. If epsilon is positive number, epsilon by 2 is also a positive number, and the same result holds. So epsilon can be replaced by any positive number whenever 0 is less than mod z minus z naught. See, z approaches z naught, and this neighborhood we shall consider as delta naught, and this is for the application of the definition for the first limit. Similarly, we apply the same definition for second limit, and mod of f of z minus w1 is less than again epsilon by 2 whenever 0 is less than mod z minus z naught is less than delta 1. So, we have applied definition for both the limits, and we say we have taken epsilon as epsilon by 2 here for both limits. Why we have taken epsilon by 2, that will be now clear, because we want to combine the two conditions, and in final condition we will obtain epsilon, and we can write this because epsilon is arbitrary. Any arbitrary means any positive number, however small it may be. Now, when both the conditions will hold, that is f of mod of f of z minus w naught is less than epsilon, and a mod f z minus w1 is less than epsilon. This holds when z is within delta naught distance, and this holds when z is within delta 1 distance from z naught, and both will hold for which value? See, z naught is the deleted neighborhood, and suppose this is delta naught, the distance, and suppose this is delta 1. Now, both these conditions will hold for which value of delta? Now, if you select the smaller value of delta, that is here, the smaller value is delta naught. It may be vice versa, or a smaller you may take as delta 1, greater will be delta naught. Anything can happen. But this condition, when the delta is smaller value, the first condition is satisfied. And what about the second condition? Second is also satisfied because delta naught is less than delta 1, and therefore in this smaller neighborhood both the condition, first condition and second condition, is satisfied. Now, what will happen for this value if z lies here? If z lies here, then that z will satisfy this condition, but that z will not satisfy this condition, because it is not within delta naught distance from z naught, and therefore we have to select the smaller of these two, delta naught and delta 1, and for that purpose let delta is equal to minimum of delta naught comma delta 1, and minimum of these two values. It may happen that this is minimum and this is greater, then we have to select delta 1. So, that is the mean. So, if we select delta as a minimum of delta naught and delta 1, then both these statement holds, or we may suppose this as 1 and this as 2. Then both inequalities hold for delta for 0 less than mod z minus z naught less than delta, and thus for therefore whenever zero is less than mod z minus z naught is less than delta, we have mod of f of z minus z naught, mod of f of z minus w naught, and this now can be written as f of z minus w1. F of z minus w1 in one bracket, and further plus f of z minus w naught. See, we can write like this. C plus, and we have f of z minus w naught, and we want to find what is the difference f of z minus w naught, and this difference we can write as f of z minus not like this, but we will find the difference between w1 and w naught. So I shall write like this, not the difference in these two, but we have what is the difference between w naught and w1, w1 minus w naught, and this now can be written as mod of f of z minus w naught minus f of z minus w1. You see this. Now f of z cancels, and what we have, minus w naught minus of minus w1, that is plus w1, w1 minus w naught, it can be checked. And now this, by properties of absolute value function, we have this is less than or equal to f of z minus w naught plus f of z minus w1. Yes, and we have proved this result earlier, or actually it is triangle inequality. We have mod of z1 plus z2 is less than or equal to mod z1 plus mod z2. If we separate it, then this is a triangle inequality, and the same thing happens for negative value. So this is by triangle inequality, or this result. And you see, what about this? This quantity is less than epsilon by 2. This is less than epsilon by 2, and the second is also less than epsilon by 2, and which is epsilon. Epsilon by 2 plus epsilon by 2 is epsilon by 1 and 2. Because whenever this absolute difference of z and z naught is less than delta, both inequality hold, and therefore we have this is less than epsilon by 2, this is less than epsilon by 2, and thus what is the result final is w1 minus w2 is less than epsilon whenever this 0 is less than mod z minus z naught is less than delta, and thus we have mod of w1 minus w naught is less than epsilon whenever 0 is less than mod z minus z naught is less than delta. Now, but we have here epsilon is arbitrary positive number, and it can be made as small as possible, and therefore we can have this value close to 0 or 0 itself. But epsilon is arbitrary positive number, or it is a small arbitrary positive number, and therefore it can be taken as 0, or that is 0 is less than epsilon. It cannot be taken as 0 but greater than 0, and because it is positive, and therefore it can be taken close to 0, and when it is very close to 0, then w1 is equal to w naught. Therefore we have w1 minus w naught is equal to 0, that is w1 is equal to w0, and thus the limit is unique. What we have assumed is limit of f of z as w0 and limit of f of z as w1 as z tends to z0, but both are equal. Thus limit of function is unique. In this way we have studied definition of limit and how to use that definition to show limit of a function is given quantity, and also we have proved this result as limit of function is unique. The problems depending on this theorem and also problems on limits, more problems on limits we will solve in our next lecture. Thank you for watching the lecture.